All right, our next topic is linear approximation. So we want to use a tangent plane that's close to a surface to provide a linear approximation of the function values near the point of tangency. All right, so what in the world is that talking about? So you have a point on your tangent plane right here, point on the tangent plane, and a point on the surface. And they're close to near, both points are close to the point of tangency. Okay, so when that's the case, so the point of tangency is over here. So we have this point on the surface right here. We have a point on the plane. So what's happening is that the plane is easier to work with, right, than the surface. So we use the point on the plane to kind of get an estimate, an approximation of the point on the surface. Because sometimes the points on the surface, due to the complexity of the surface, can be really difficult to find. But we can use a point on the tangent plane to get close enough. So that's the idea. There, I just wrote it up. So we use the point on the plane, which is easier to work with, right? Planes are pretty easy. So we'll use that point on that plane to approximate the point on the surface. All right, let's do an example. We have a function f of xy equals the square root of x squared plus y squared. And we want to use a linear approximation for f of 3.06 and 4.1. Okay, so let's start off. First thing we need to do is choose a point of tangency that's close to this point, right? So this is point P, right? Point P is 3.06 comma 4.1 comma something that we don't know. That's what we're trying to figure out, right? So our step one will be to choose a point of tangency, right? A point that is close to that point that we're looking for, which I think is pretty obvious for this case. It's going to be 3, 4, right? So that's what we're going to choose, 3, 4 for x and y. And technically there's some z component to it, but we don't know what the z is. That's kind of what we're dealing with. So it's 3, 4 something, if you will. But it's the 3, 4, this part that matters. Okay, next we're going to find that tangent plane, right? Because we need the plane to be able to do this. So find tangent plane. Okay, well, to find the tangent plane, we need a couple things. We need a point. So we're actually going to have to find that third component. So z is equal to f of xy is the square root of x squared plus y squared. So therefore, z is equal to f of 3, 4 would be the square root of 3 squared plus 4 squared, which is the square root of 25, which is 5. So our point is 3, 4, 5. This is the point of tangency. Right, so I knew that I wanted the 3 and the 4, and now I figured out I'm going to have the 5. So you could do that all in the step 1 if you wanted to, and then kind of find the tangent plane down here. As a matter of fact, I think that's exactly what I'm going to do. So I'm going to let this part be the point, and then I'm going to find the tangent plane. Okay, so to find the tangent plane, we need the normal vector. So the normal vector is the gradient of w, but we need w. We don't have a w. All right, well, let's figure that out. So we know that z was equal to the square root of x squared plus y squared. Therefore, if I subtract z from both sides, or you could subtract the square root of x squared plus y squared from both sides, it doesn't make any difference. You'd get 0 equals the square root of x squared plus y squared, take away z. This is now your w. All right, so over here, for the gradient, I would take this the derivative with respect to x, the derivative with respect to y, and the derivative with respect to z. Okay, well that's going to be a little trickier to come up with than you might think, because this is really, if I rewrite this, this is x squared plus y squared to the 1/2 power, right? So this is w. I'm just going to kind of put that over here because it's kind of on the side. All right, so to find the derivative, we are going to need chain rule, and a lot of it, because we're going to have to bring the 1/2 power down. So 1/2 times x squared plus y squared to the negative 1/2 times the derivative of the interior with respect to x, which is 2x. Then we're going to have to do it again. 1/2 x squared plus y squared to the negative 1/2 times 2y. And then luckily for us, the derivative with respect to z is really easy. It's -1 again, so that's nice. So let me rewrite this. Well, actually, I don't actually care. This is fine. So this is the gradient at all points. So the normal vector at all points. But of course, that's not what we want. We need the gradient at our particular point. So the gradient at 3, 4, 5 would be, all right, so I'm going to plug in the gradient of w at 3, 4, 5 equals, all right, 1/2, the 2's are going to cancel, so it's going to be x divided by, so 3 divided by the square root of 3 squared plus 4 squared, right, because the negative will make it in the denominator. So the square root of 3 squared plus 4 squared is the square root of 25, again, which is 5. And then for the y component, it'll be 4 over 5. Right? Again, this denominator is going to turn into the same thing we saw up here. Square root of 3 squared plus 4 squared is indeed the square root of 25, which is 5. So these denominators are going to be this, and the 2's are actually going to cancel because it's 2 divided by 2. So it's really just x over this and y over this, and the square root of 25 is 5, and then -1. Now this is perfectly fine, and we can use this. It's not so helpful. So what a lot of times we will do, so let me write the plane. So the plane could be written as 3/5 x minus 3 plus 4/5 y minus 4 minus 1 times z minus 5 equals 0. And that's fine, but it's not so useful and easy to work with. So what we can do is multiply everything. And you can do it up here with the vector, or you can do it down here later. It doesn't really matter. But you multiply everything by 5 to make the common denominator. And that'll turn it into 3x minus 3 plus 4y minus 4 minus 5z minus 5 equals 0. That is the easier plane to work with. All right, now for the last bit. So we've got step 2. So now step 3, we have to do our approximation. So use the plane to approximate. Which is not as hard as you might think. All you do is you take the x value you actually had, which is 3.06, and you substitute it in here. So you go 3 times 3.06 take away 3 plus 4 times 4.1 take away 4 minus 5 times z. Z is what we're looking for, minus 5 equals 0. And we solve this with a calculator for z. There, I just popped over to Maple. And I figured since it's basically glorified algebra 1, I mean, I just made Maple solve it. I said, you know, but type in this equation, solve it for z for me. And it gets 5.116. Now, the actual value, if I take the function and I put those actual numbers in, is 5.116 and then some extra bit at the end, right? So they're not exactly the same, but this is easier to work with mathematically than this particular function. But over in my paper, I'm just going to note that. Right? So Maple came up with the solution for me, and it's 5.116. And that's the approximation. right? Oh, and because we want to prove this is an approximation, we would actually put all the zeros afterwards, right? It doesn't have those extra decimal places. So unlike the actual solution, which had the extra decimal places.